So for our first presentation on Introduction to Artificial Hearts, this is being presented by Associate Professor Shaun Gregory. Associate Professor Shaun Gregory is a cardiovascular engineer with a specific focus on the development and evaluation of mechanical circulatory and respiratory support systems, or artificial hearts and lungs. His research is focused on device development, fluid mechanics, physiological control, infection resistance, prototype manufacturing, device evaluation, and even more. Shaun works between academia and industry in an effort to translate his research. He leads a research group based at the Baker Heart and Diabetes Institute, where he brings engineers, scientists, and doctors together at the bench side to develop new medical technologies to improve patient care. Shaun also leads and contributes to the leadership of multiple national and international projects, groups, and societies. So without further ado, Shaun, feel free to share your slides and begin your presentation.
Thanks very much, Ethan, for the very kind introduction. All right. So thank you very much for inviting me to speak today. I'll be giving an introduction to artificial hearts. So I'll go through, first of all, why we need them, what artificial hearts really are, and what we sort of can call artificial hearts, some of the limitations behind them, and some of the ways that we're looking to address those limitations. So first of all, if we look at cardiovascular disease and heart failure, I mean, the number one thing to say here is that cardiovascular disease is the leading cause of death globally. It kills more people than all forms of cancer combined. There's an estimated 17.9 people died from cardiovascular disease in 2019, which is 32% of all global deaths. And there's a global prevalence of about 500 million people. Heart failure is kind of what the end stage of cardiovascular disease can lead to. That's when the heart is no longer pumping enough blood to move around the body for what the patient needs. And that affects around 64 million people globally. The gold standard treatment for heart failure is a heart transplant. But unfortunately, there's only about 8,500 of those performed globally per year. So there's a huge discrepancy between the supply and the demand for donor hearts. So that's where mechanical solutions are required to support the heart and the circulatory system. But before we talk about those mechanical solutions, let's just have a look at what the heart is as an organ, why it fails, and a few little terms that I'll be using throughout the presentation today. So if we think about the way that blood flows, so blood comes back into the heart from the lungs via the pulmonary veins, enters the heart into the left atrium and goes through a heart valve called the mitral valve, into the left ventricle, where it's then pumped out under quite high pressure through the aortic valve into your aorta, which feeds oxygenated blood to the brain, the body, all of the organs. This is where the body then gets its oxygenation from and then releases carbon dioxide. And then that deoxygenated blood is then returned from the upper body via the superior vena cava and the lower body via the inferior cava into the right atrium. The blood then passes into the right ventricle, and then gets pumped out into the lungs via the pulmonary artery. In the majority of patients with heart failure, they have failure of the left side of the heart. And that's because the left side of the heart has to do a lot more work. It has to pump blood at higher pressure and a lot further. So that's why it usually fails. So if we then look at the devices that are typically used to treat that we call artificial hearts. Now, there's 3 devices that can kind of fit into this category. You've got the total artificial heart, which is really an artificial heart. When you think of an artificial heart, that's what we're often talking about, a total artificial heart. Then we've got a ventricular assist device, and then we've also got extracorporeal membrane oxygenation. But I'm going to briefly explain what each of these 3 are and the differences between them. So if we first of all look at a total artificial heart, this device essentially completely removes and replaces the native heart. So the patient's chest is opened, their heart is removed, and a device is put in place of their heart to keep you alive, to keep blood pumping around the body. These devices are typically used for medium-term use. They rely on technology that essentially, if we look at the device in the image there, they're essentially balloons within chambers. And those balloons are essentially squeezed using compressed air from an air compressor outside the body, which pushes that compressed air in via those tubes into those chambers to squeeze those balloons to kind of make it like a heartbeat. And, you know, if you imagine squeezing a balloon 80 times a minute for an entire year, that balloon's going to wear out pretty quick. So that's why they're used for medium-term use, months to maybe a couple of years at best. They have saved a lot of lives, but they do rely on this sort of older generation pumping technology. And they are typically quite large. They won't fit in all patients. The devices are quite noisy and they certainly limit patient mobility. You know, these are quite sick patients and are going to have to carry around about a 10 kilogram air compressor with them. But the next generation of devices for total artificial heart support use different pumping systems. They're called rotary blood pumps. And they essentially use sort of like your fish tank pumps that you might have seen, where it's an impeller that spins around really fast. That's the kind of technology that they use. But until we get to that stage, there's very few implants happening globally per year for total artificial hearts. So the majority of the devices that are implanted are actually ventricular assist devices. Now, these aren't really a total artificial heart. They don't completely replace the heart, but they do assist the heart. So in this case, the heart is left in place and a pump is added in parallel. So basically it sucks blood out of the left ventricle, spins it around very fast and pumps it out into the aorta. Now, if you have a look at this figure down the bottom right here, that's a bit better detail of how these pumps work. So the blood comes in from the left ventricle. It's rotated around via, in this case, a centrifugal, but it can also be an axial pump. And this centrifugal pump has magnets that levitate and rotate the spinning impeller to pressurize the fluid and push it around the body. That fluid is then pushed out via a graft into the aorta. And in this case, the pump is completely electronically driven. The total artificial heart I showed on the previous page has compressed air getting pushed into the body. This one here just needs a power supply via a fairly thin cable that comes through the skin, and the patients wear a controller and battery pack outside. This long-term durability of the devices and better comfort of the devices means that we can get long-term use. Patients have been supported for greater than 10 years on these devices. They're typically small, fairly quiet devices that allow patients to return home to some sort of quality of life that they had before. Not as good as a transplant, but they can do many activities. And there's typically thousands, a few thousand of these devices being implanted per year. But it is quite an invasive implantation procedure, and it usually has to be planned. So in the event that a patient needs really urgent support of the heart and or lungs, these patients would go on something called ECMO, which is extracorporeal membrane oxygenation. Again, in this case, the heart is left in place and it's assisted by a pump to take over for the function of the heart, but it also has an oxygenator to take over the function of the lungs. So the way ECMO typically works, if we look in this figure here on the right, we have, in this case, a tube is placed in the leg or sometimes in the neck, and then blood is drawn out via a pump, pumped through an oxygenator, and then pumped in via the other leg or the neck. This takes over the function of the heart and the lungs and can be used for days and even up to months. And this is typically used while they're waiting for a transplant or waiting for a more permanent device. So clinically available devices use the same similar sort of durable pumps that we saw with those VADs, but with the requirement for an oxygenator, it does make the systems a little bit less durable because oxygenators get blood clots in them and they just don't really last as long as the pumps do. It is a less invasive implantation though, which is useful for getting these patients supported very quickly, especially if someone's had, say, cardiac arrest in the hospital or even out in the field. They can implant ECMO very, very quickly and keep patients alive. And again, there's thousands of these implanted per year around the world. So let's have a look at the survival of these devices and how that's evolved as well. So if we take ventricular assist devices, for example, there's thousands of them implanted, so we've got pretty good data on survival with these devices. If we look at the biggest study that examined survival about 20 years ago, in 2001, what we saw was that patients on medical therapy, so this is without any of these devices, mechanical devices, treated with pharmaceutical drug options, they had a 1-year survival rate of about 25%. So 75% of patients were dead after a year in this category. Whereas when we added these old generation left ventricular assist devices, not the newer advanced ones, we increased that survival twofold to 52%. So 1-year survival, 50%. At the time, that seemed really good. But then as engineers developed more complicated but much better pumps, more durable devices that can pump blood around the body, what we see now is our 1-year survival rate's around 86%, which, although that means about 14 patients have passed away after a year, it's still quite incredible to think that these are the sickest of the sick patients that you can imagine, and 86% of them are still alive a year later. So we've certainly come a long way. And if we compare that with heart transplant, which is the gold standard therapy for patients with heart failure, heart transplant has an 85% 1-year survival. So our 1-year survival with these mechanical pumps has actually met or exceeded that of heart transplants. But it is also still important to note that survival timeframes with a ventricular assist device or artificial heart are really only up to a maximum of about 10 years so far. We haven't really stretched much beyond that. Whereas transplants, we have survival data up until about 20 years. So we know that a transplant can support you for a very, very long time. If we look at ECMO, on the other hand, you know, that one that's outside the body, the survival is far, far poorer. In fact, in a lot of patients, the 1 year, or even the 90-day survival is in the range of 25%. So ECMO is usually used for the absolute sickest of patients. It is really a life-saving therapy, and it still has a lot of improvements to be made to the technology to bring those survival numbers up. So why do patients die on these devices? What are the main complications? Well, interestingly, they're pretty much the same with all three forms of technology. So total artificial hearts, VADs, and ECMO all have the same problems. And it's probably because the technology behind them is relatively similar, and the patients that they're treating are relatively similar. So the main complications that we see with these patients are thrombosis or blood clots, lots of bleeding, probably because of the big surgery. Infection is a big one because you have something crossing the skin for a very long time. Suction events or the inability of the devices to really control the blood flow to meet what they're meant to be doing. Quality of life, the quality of life for these patients is generally quite poor, and a lack of clinical training. The implantation of these devices is typically only performed in very large central hospitals, cardiac hospitals, where they are very high-level trained people or clinicians. So we need to extend that training. We need to get clinicians better trained at doing these things. So how do we improve our devices? How do we lead to the next generation of essentially artificial hearts that can really help more patients? Well, the way that we're doing that, at least in Melbourne, and a lot of other places are doing a similar approach, is to bring engineering and medicine together in the one place. So having, in our case, a cardiovascular engineering lab in the big transplant hospital in Melbourne. We're very, very lucky that our laboratory is based here on campus of the biggest heart hospital in our state. And we can then use that to improve patient outcomes through the development of improved technology. And I'll go through some of the ways that we're using engineering technologies to resolve those clinical problems. So if we think back to those main complications I said before that are in that big circle in the middle, thrombosis or blood clots is one of them. Now, we know blood clots for a few different reasons. One of the reasons is because it doesn't move correctly. You know, if you think about if you cut yourself, if you bleed, if the blood is just stationary on the outside of your body, it will clot quite quickly because it's not moving. It's the same thing inside the blood vessels as well. If the blood's not moving, it typically clots. So this is where we can look at how do we design our devices to keep blood moving, to prevent it from clotting. And to do that, we can actually use the same techniques that are typically used when you're designing a race car or a high-powered rocket. And that's using computational fluid dynamics. So what we do is we take CT scans of patients that have these ventricular assist devices or that need these ventricular assist devices. We then extract their geometry of their heart and we model their heart. So in this case, we've got the left atrium, the left ventricle, and the aorta. Then we can use these computational fluid dynamics softwares, this really complex engineering software, to model the blood flow within the heart. In this case, you can see a large jet of blood flow coming in through that valve, swirling around in the heart and then getting sucked out by the device. And then we can think about, all right, what happens if we change the angle that we put the device in? What if we insert the device a little bit further? Or what happens if we change the geometry of that device? How can we reduce the chances of blood clots forming? We can then take that to the next level and actually predict where blood clots will form, as we've done in our computational models. And then we can also take that to the next level and test these devices with real human blood and work out exactly where and when blood will clot and how we can improve that with better devices. We can also reduce bleeding complications using engineering techniques. So bleeding often happens because the patient undergoes a very long surgery. They're on a heart-lung bypass machine. It's very invasive. There's lots of sewing. Essentially, the way these devices are usually implanted is they make a big hole in the heart using something that resembles an apple corer. And then they put the device in and then they extensively sew it onto the heart. So we're working on using engineering techniques to make that quicker. Now, we can connect a hook on the wall much quicker than you can attach these valves. We can attach a gate latch, things like this. So there's lots of mechanical concepts that we can adapt for surgical applications. And that's exactly what we're doing. So in this case, we've adapted something called a hollow wall anchor, which is essentially a way of hanging a picture on a wall to make a rapid surgical fixation technique for a ventricular assist device. So this means that basically what happens is rather than the doctor having to open their chest, put them on a heart-lung bypass machine, make a hole in there, do lots of sewing, close it up, have a bit of bleeding. In our case, we can do a little smaller incision in the chest, push our device in, pull a little lever out, and all of a sudden the device is attached in about 30 seconds. It prevents lots of complications in the patients and gives them much better outcomes. So we're working on that. We can also use engineering techniques to reduce infection. So infection is really common in these devices. And if we think about why that happens, it's really easy to understand. Some people go ahead and get their ears pierced and then their ears get infected because they've got something crossing the skin there. Now that's only a tiny little hole in your ear. So you can imagine how bad the infection might be if you've got something that's 5 to 10 millimeters coming out through your stomach and constantly within the ears. Lots of opportunities for bugs, for bacteria, to migrate into that hole and even go further into the body. So we first of all wanted to look at why that was happening and how we can stop that from happening. And we think that the best way to stop that from happening is to encourage the skin cells and all of the body cells to fully integrate within the device to close the hole so that no bacteria can actually get into the body. So what we did was we first of all created skin in a dish because we can't just practice doing this. We can't do experiments on humans. So we made this skin in a dish and it's really quite cool. It's made from tummy tuck discards and we basically recellularize it. And essentially what we end up is with a piece of what is essentially human skin in a petri dish, where if you cut it, it moves. It's really quite incredible. Then we took the surfaces that exist on these current devices with that cable that crosses the skin. Now those surfaces are a very smooth polyurethane surface and also a woven, sort of felt like Dacron. If you can imagine that the surface of a pool table, it's very similar to that. It's this woven fabric. And we looked at how the skin cells were growing into that. So basically what we saw were the skin cells very happy to grow up to the polyurethane surface, but they just can't attach to it because it's too smooth. Right? Cells don't like attaching to something that's too smooth. The Dacron surface, on the other hand, this woven surface, the skin cells loved growing up, growing into it, weaving into it. But what we found was that the pores, the gaps between those woven surfaces were just too big for the skin cells to actually bridge across. So we figured we needed something in between. We needed something woven, but something that had a very finely controlled mesh that skin cells will love and grow across. So that's where we use a process called melt electrowriting. Now, melt electrowriting, if you think about it, is essentially micro 3D printing. You've got a little nozzle with a high voltage and a polymer in there, and you're essentially extruding that out to create a shape or a scaffold, however you want. And an example of that is down the bottom left here. This is the scaffold we created, so it's kind of like a very finely controlled mesh. And then we evaluated that in a very large series of preclinical models, and we found essentially that the mesh that we created encouraged skin to grow in it. The skin cells could bridge all of those gaps and really grow in. And we could even make it biodegradable, where that mesh will eventually just biodegrade, go away, and leave you with this really nice skin device interface. And so we've proven it works, and now we just have to get it to work in humans and get this sort of technology included in current devices. Moving on then to suction and quality of life. So essentially, what your body does is it constantly adapts its rate of the heart beating and its force of contraction of the heart to meet what the body needs. A really good example of that is if you wake up in the morning, your heart's usually beating quite slow, your pressures are quite slow, it's not beating very hard. And then if you decide to go for a morning jog, what happens is your heart then starts beating harder and faster to deliver the blood flow that you need. These devices don't do that. They run at one speed. So these artificial hearts, essentially, what happens is the clinicians implant them, they set them to a speed, and then they send the patient home. So you're essentially constrained to almost having one heartbeat, which is really limiting. If you want to go for a run, it can't increase the blood flow you need. If you want to go to sleep, it can't decrease that. So patients will feel faint if they stand up too quick. They'll feel faint if they walk upstairs too quick. They might have, complications because of all of this. So what we're doing to address that is creating sensors that detect what the patient is doing. Very easy to do that. We can create these sensors. And then we use those sensors as feedback to develop control systems to automatically change the way that the pump runs to meet the body's demands. Now, as an example of this, we use the sensors that are implanted in the heart. The only problem with that is that they need to be implanted for 10 years and they can't have any drift. So the sensor technology is not quite there yet, but the controller technology is. So as soon as we can develop sensors that can detect what patients are doing, that don't drift and are very, very reliable for 10 years, then we'll be able to make devices that will be able to keep up with what the patients need. And then one of the last things we're doing to reduce those complications is improving clinical training. So in this case, we're developing a series of training modules to help clinicians get better at what they do. So we can develop simulation training on a computer. So these are virtual patient environments where the clinician can see the pressures and the flows and all of that kind of thing. And they can change the way the pump is running. They can give the patient virtual treatments, and then they can get really good responses out of it and learn what will happen to the patients. We can also develop task trainers, so practice surgical tools and practice surgical patients. So we can make a fake chest, for instance, and make it so that the surgeon can practice on that fake chest. We can also create these models in augmented and virtual reality environments too, like what you see on the bottom right there. This is an augmented reality environment that we created recently of an intensive care unit, where we've got a patient on a bed and we've got the device there. We've got all of the clinical controllers around that. And then the clinician can go up and practically treat the patient. They can see help menus and get instructions on how to do this and get very well trained in how to treat these patients. And again, this is all using engineering technology. So this really demonstrates how essential engineering is to improving clinical medicine. So where to next? We've got these pretty good devices now, and we're making these incremental improvements, but where will we be in 2050 is the question. What is the future vision for this technology? And in my opinion, the first thing that we're going to have is minimally invasive implantation. At the moment, the devices are implanted through literally cracking the entire chest open and implanting the devices. It's very invasive, and older patients just can't withstand surgeries like that. But we already have devices that can be implanted in the legs, such as the Biomedical Technologies. So these devices are literally put into the leg, put into place in the heart, and then left in place. The problem is they still come out of the leg, which means that when you've got the device, you can't walk around. You have no real mobility. So we need devices that can be implanted, for instance, through the leg, but then where the introducer can be removed and the device just stays in there. Similar to what we have with heart valves now, how you can implant heart valves through the leg. And one way to do that is to make devices that can actually fold up and be implanted. So a device that can be implanted with, say, a 5mm diameter for the implantation, where it's fed into place via the leg in biomedical imaging. Then when the introducer is removed, it expands, and then it starts running with a power system that can cross the chest without cables, is where I think we'll be in 2050. But that power system crosses the chest without cables is incredibly important. So as I mentioned before, these devices have that cable that comes through the skin, definitely has lots of chances for bacteria to move along it. It's also a bit annoying for a patient to have a cable crossing their skin. Now, many of us are very familiar with transcutaneous energy transfer systems, even if you don't know the term. Now, transcutaneous energy transfer essentially means the transfer of power without wires. So we can take our phones and we can put them on a mat and it will charge them. We can do that already. And so why can't we do that with a medical device? Well, we can, but the problem is that if your phone doesn't charge correctly, that's okay. You can plug it in, no problems. Or you might be able to survive a couple of hours without using your phone. If your artificial heart doesn't charge correctly, you can't survive. You literally will die on the spot. So making systems that are 100% reliable, that work very well, that don't transfer too much heat into your skin, that are still comfortable, there's still a few avenues to overcome to get these devices working properly. And the other thing is going back to that physiological control concept I said before. So really having these devices respond exactly like the human heart responds. So essentially having an autopilot or a driverless vehicle for these devices where we can implant them, they detect what's going on, they change their performance just like our native hearts do to meet exactly what we need. That's definitely in the pipeline for these devices. So now moving on, how do we test them? So when we develop these improved devices, how do we actually prove that they work? And what are the methods to show that it's safe in patients? Well, typically that we go through a really long period of preclinical evaluation when we're developing these artificial heart devices. So we start off with something called lump parameter modeling, then we go to simulations, then we go to virtual anatomic fittings, so essentially checking if it fits in the chest. Then we test it on benchtop systems that represent the heart and circulatory system. Then we test it with blood, and then we test it in animals. Now, it seems as though this is a real one-way process, but it's not. It's important to note that this is an iterative process, and you might move along that development pipeline, but then you might have to go back a little bit and then continue along that pipeline on some occasions. So if we look at each of those in a little bit more detail, the first thing is lump parameter modeling. Now, this is, I know what you think, super simple, right? Not a complex diagram at all. Well, this is an example of a lump parameter model of the circulatory system. So what we essentially do here is we mathematically model the heart and the circulatory system, and then we mathematically model your device that you want to implant, and we combine the two and see how they respond. So in this case, what this shows is what we can do is we can break the blood flow up into, and the blood vessels up into their various physical properties. So they have resistance to blood flow, they have compliance or stretchiness, and they also have an inertial property. Apologies for that. So that's what this essentially does. It breaks it up into those components. And we can have left heart and right heart. We can have different blood vessels. We can break that up into the lungs. We can simulate breathing and all of these sorts of things. And then we numerically model a device and we put it in there and we see how well it will work. It means that we can rapidly test a new device in a variety of different conditions very rapidly at very low cost. So it's usually a typical way to start off developing these devices. We then typically move to other simulation models where we essentially have computational fluid dynamics or fluid structure interaction models to look at the blood flow that might come out of our devices or the blood flow within our devices. So this is an example on the left that you can see here where we've taken a CT scan of a patient, in this case on ECMO. We've shown that the blue here is blood flow that doesn't have any oxygen. The red is the blood flow that has lots of oxygen in it. And we've determined that by changing the position of the tube that goes into this patient, we can deliver that oxygenated blood up to the brain. So it's a way of using essentially blood flow simulations to really determine how well our device works. And the beautiful thing about our computational models now is we have this amazing computational power where we can resolve these fluid dynamics in incredible detail. As you can see here, we can see exactly what's going on with this fluid flow to determine exactly where blood might clot, where blood cells might get damaged, and so on and so forth. We can even now model blood clots forming and being released in different geometries. So you can see on the left here, we've got a blood clot that's formed in this vessel, and it's showing and being released, and for instance, going to the brain and causing a stroke. On the right here, we've got a backward-facing step, and you can see this blood clot's forming, and then elements of this blood clot are now being released into the circulation. So these are the kind of things that we can incorporate into our device development to make sure that we don't have those blood clots forming and being released, to make sure that these patients aren't going to die. So our computational modeling has advanced substantially. If we then go to virtual anatomic fitting, again, sticking on with that computational theme, we can take data from patients and virtually implant our devices into those patients. A really good example of that is some software by a company called Autonomy. They've developed this software where they have literally thousands of patient data sets built into their software, where they can very simply extract those patient data sets. They can do statistical modeling on those patient data sets to show, with a heart valve of this size, you typically have a ventricle of this size, things like that, where you can then use that to develop your device. You can refine your device, you can virtually implant it, you can simulate your device being implanted or the blood flow through your device, and you can also then get reports for your regulatory compliance. So there's softwares that are emerging, like this fantastic piece of software here, where you can really start to accelerate the development of your devices. The next stage in moving out of that sort of computational phase of your projects or the development of these devices is to do tests on the benchtop, to do hydraulic testing of your device. Those simulation models are great, but one of the problems with them is they're typically quite idealized. They obey the laws of physics, but only the physics that you put in there. And so it's very hard to model absolutely everything that you experience in a real world scenario. And that's why we move to these more complex benchtop models. So in this case, this is called a mock circulation loop. Essentially, it's a mechanical representation of the heart and the circulatory system. So what we see here is we've got the left side of the heart, the right side of the heart, the body, the large blood volume in the body. We've got the lungs, we've got the blood flow to the heart, the blood flow to the brain, the heart valves. All of these things are included in a physical model of the circulatory system. If you press start on this model, you actually see the heart beating. As you can see, it produces pressures, in this case, pressures that are extremely similar to what you can imagine any patient having. And you can essentially simulate any patient that you can imagine in the hospital. We then have implemented autoregulatory responses in there, just like your normal heart has. I spoke before about how you get up and you go for a jog and your heart beats faster. Well, that's called the Starling response, and that's exactly what's imitated with these lines here. You also have autoregulatory responses where your body automatically adapts how the blood flows to different vessels. And we can simulate that in our benchtop simulations as well to get incredibly realistic simulations of a patient without actually having to test in a patient. This means that we can refine our devices, refine before we go to animal or human studies to make sure that we have the most reliable devices first, so that we can save animal and human lives. We can then also test our devices with blood. This is a great example of a blood circulation loop, some tests that we do, particularly with a group of ours in Queensland, where we essentially take our device, we put human blood typically in it, and then we evaluate how that device responds to blood. Does it stretch open these blood cells? Does it break them apart? Does it result in blood clots throughout the device or throughout our mock circulations? What happens with all of the blood properties within these devices? And we can evaluate them incredibly thoroughly now in a benchtop setting, again, before we go to animals or humans. And then finally, we unfortunately do have to go to animal studies sometimes. So these preclinical models are very complicated. The animals are treated in the absolute best way. They have the best clinical staff managing them. They have the best operating procedures, operating rooms, facilities, you name it. But we do unfortunately have to use animal studies for our devices. To do that, we have to model the clinical condition that we're treating, that we're trying to address. So in the case of the artificial hearts, we need to model chronic heart failure and heart transplant models. We need to have all of the assessment criteria in there, the imaging, the analysis equipment in there, and so on, to do very extensive evaluation in a model that is as close as what we can possibly get to a human. So thinking about all of that and all of the engineering advances that we still need to make in this field, because there are so many, we can make these devices substantially better than what they are at the moment. So how can you help? How can we as student societies, as groups of students from around the world, help to advance this technology? Well, that's something that we thought about a couple of years ago. And so that's why we came up with something called the Heart Hackathon competition. And Ethan, one of the chairs today, is critically involved in this competition. He's done a brilliant job in this as well, as have many of the people in the team. And it was founded by myself and launched with the help of the Monash MedTech Innovators. And we've also got sponsors, including Syncardia, the only artificial heart company in the world, Hydrix, Magasys, ISMCS, and now also our Real Heart have come on board as well. So I'll give a little bit of a very brief description just to wrap up my talk about the Heart Hackathon. So this is an international student competition developing the next generation of artificial hearts. So many of you are probably from technical universities, or some of you are probably from technical universities, where you might have seen these international student competitions before. You've probably seen, one of the more common ones is this Formula SAE competition, where essentially students develop, prototype, and build these race cars, and then they take their race cars around the world and they race against each other, essentially doing time trials. And the winners get a prize. They also have these for Mars rovers and high-powered rockets and so on and so forth. And all of these really big competitions have a very complex concept that is continually improved year on year, and then students compete year on year against each other. But there's a real lack of medical engineering design competitions. So that's where we came up with Heart Hackathon. So this is an annual international competition where student teams from around the globe will design, prototype, and test their total artificial heart solutions to support a simulated human circulation. So students will compete against one another at the annual ISMCS symposium. So rather than having an independent event, we've teamed it up with a big conference in our field to get the best benefit for everyone out of it. And the best student teams will get prizes for the best total artificial hearts, and also an accompanying commercialization plan. We felt that having a commercialization plan was particularly important because we want students to learn not only the real technical skills about how to build an artificial heart, but also those skills about how to commercialize a medical device. So that way then you have that experience when you're going into industry. And then student teams will then use the feedback that they get from each event to improve their total artificial heart device for future competitions. So it's really a marathon. It's meant to be year after year after year after year, iterating, developing, further prototyping, improving your total artificial heart to get the best possible device. So the way that it works is that teams form at universities around the globe, supported by academic supervisors. There's lots of teams that already have formed and registered for the competition, so we do encourage you to really get moving if you want to do this, get it done very, very soon. Teams will then design, prototype, and evaluate their total artificial heart and develop a commercialization plan and register their interest by October 1st this year. So the deadline for registration is very quickly closing. If you think you might be able to get a team in, then please register. You don't have to get all of the team names in there. You can still build it afterwards. That's absolutely fine. But if you want to get involved, please register ASAP. We're then going to have a virtual competition event, which is more just going to be about the designs that we've come up with at the start of December. We're not expecting teams to have had actual physical devices working by then. Teams will then submit a preliminary report in March next year, which is then assessed, and then the finalist teams will be announced in May, where those finalist teams will then submit technical progress and commercialization plans in August and present at the annual competition at ISMTS in the United States next year. There's a huge amount of benefits to getting involved in a project like this, particularly for students. It's a unique learning experience. They'll get experience designing, prototyping, and testing a medical device, and developing those technical research and business skills, and also those soft skills of working in a team, being a professional. It'll also give them connections with employers, which we hope will lead to a lot of jobs in this field. The industry, it gives a brand exposure and access to the best and brightest young students, and also the best academics in this field. And for the academics, it gives them links to industry and also the best students. And for the conference, it builds our community and has a really exciting new event. We've developed lots of support to help the teams. This is a brand new competition, so we understand it's daunting. We've developed the competition announcements, scientific overview. We've got really detailed documents on what a total artificial heart is and what the complications are on the website, ready to go. We've got competition rules and supplementary regulations, IP policies. Most of that's available now. If it's not on the website right now, it will be very soon. Same thing with marking templates and criteria and entry forms. We'll also be delivering online workshops throughout the whole competition. These will be workshops from industry and academic professionals teaching you what is a total artificial heart, how do they work, what are the complications, just like you've seen today. How do we build them? How do we test them? And so on and so forth. So there'll be plenty of online workshops to help with that. Some of the questions we often get asked, first of all, are there prizes? Well, yes, of course. First prize is $2,000, second $1,000, third $500, and there'll also be a special prize for $500. The expectations are incredibly realistic. Year one, we're expecting really basic prototypes on the bench. You know, these aren't going to be small devices that can fit into any human. These are going to be very, very basic pumps. But by year 5, what we're hoping for is quite refined prototypes where it's something that you could imagine actually implanting into a human. The team requirements and configurations, there's no limits on size, but there is a maximum 20% of the team can be a PhD student, just to make sure that there's not too many high-end students, that we're really encouraging the younger undergraduate or master's level students to get involved. Teams will need to organize their own sponsorship funding. We can help you with instructions of how to do that, and sometimes with links to sponsors as well. For the submissions, we would expect to see things like team information, designs, test procedures and results, and your commercial strategy, of course. And if you have any other questions, you can feel free to contact us. Here's our website for the Heart Hackathon, and also my personal email as well, Shaun.Gregory@Monash. Please do visit the website for the Heart Hackathon. It's a really exciting competition. I'd love for you all just to learn a bit about it. Register a team if you think that you might be interested. Get in now, because there will be a cutoff and a limit to the number of teams. So please get involved. And with that, I'll stop talking, and I'm very happy to answer any questions you might have. Thank you.
Thank you very much. So yes, if you have any questions, feel free to put up your hand, put in the Q&A or chat. In the meantime, one of the things I was curious about was, in the current simulation modeling, how much of that is used currently in clinical practice to inform device selection or how you implement it in the surgery?
Really good question. Typically, it hasn't been used a lot in the past, mostly because if you have something like a piece of software, for instance, that you're using to define and to guide how you implant a medical device, then that software actually has to be classed as a medical device itself. because it's informing clinical practice. It's informing like the way that a patient will be treated. So officially, they're not typically used for that. Unofficially, there might be a little bit of use happening. But what we've done is we've done simulations, for instance, to show that hey, you should be implanting the device a little bit further in, or you should be angling it a little bit better way. And then we publish a research article on that. And then we send that research article to the clinicians. And the good thing is that the clinicians trust us as engineers, and they do adopt that in their clinical practice. Now, that's not us telling them that they have to do it or really anything like that as far as a medical device regulatory standpoint. It's the clinician making a decision based on research that's being performed. So that's usually the best way to do it, is do it via a research pathway and then inform the clinicians through that.
Okay. We have one question submitted, which was, my university has an existing team for the Heart Hackathon. Is there a standardized way of contacting existing student teams?
Do they mean other teams or our Heart Hackathon organizing team?
That I'm not sure. If you're comfortable, feel free to put your hand up and we can let you talk. But let's assume that it's both, and we'll answer both parts of it. Yeah.
So to contact the Heart Hackathon organizing team, definitely just jump on the website. There's contact information on there. To contact other teams, we don't have that at the moment. So we don't have team-to-team communication. We're keeping that relatively confidential at the moment. But I would encourage you to obviously build up your own team, contact students that are within your university, particularly use your academic advisors to get that message out is one of the important things that you can do. Yeah, that's probably the best way to do it.
Yeah. So our plan is, once the official competition starts in October, that we will invite all teams to join a Slack group where you will be able to meet and communicate with other people. Which will be a bit more difficult is we do hope that people attend the webinars live. For instance, in our kickoff event, we're planning for an ideation sort of workshop where we get teams to mix and meet up with each other, look at the current problems, which Shaun highlighted in his presentation, and then do some quick ideation so that you have some broad ideas of potential avenues that you may like to go for the rest of the year. But the hope is that within these workshops that there will be a bit of a networking opportunity, but admittedly virtually. Yeah.
But definitely for the first event in person as well in the States at ISMCS, there's going to be some great networking opportunities, an opportunity to see what all of their other artificial hearts look like, and of course accompanied by plenty of drinks and food opportunities to network with your fellow student teams from around the world.
Definitely. But this is more future years. We can comment more specifically in Victoria because that's where this competition is arising from. We do a plan to have in-person events to meet other teams and things. For other countries, it will depend on the sponsors we find and if there are a lot of teams there. Yeah. Another question I had was, you mentioned being inspired by ideas that are outside the medical field, that were potentially implemented already successfully. How does one, wanting to be an innovator, come across these ideas, like actually find them and try to translate them into medical practice?
That's such a good question, Ethan. I wish I could answer that really well. I think that for me, my career is kind of a big part of my life. Ever since I was really, really young. So when I was an undergraduate, I did my final year project in, my honors thesis in testing artificial hearts. And I loved it. I love what I do. And then I did my master's and my PhD in it. And I've been involved in this field for almost 20 years now. And so I kind of live and breathe this field. So when I take my dogs for a walk, I will be looking at the latches on the fence or a pole or all these mechanical things. Or when I renovated a house a little while ago, everything I did, I always thought, how can we apply this back to a surgical application? And so I think having an understanding of all of those different mechanical concepts, and even just going to your local hardware store and having a look around at all of those different concepts is really important. But then having an understanding of the medical need as well is incredibly important. So integrating yourself within a clinical environment. And that's something that I've been very lucky in my career. I've always worked or directed laboratories that are in hospitals. I've been very lucky to see many surgical procedures and visit many patients and their caregivers and find out what the problems are. And a lot of the time, it really is just that, about going into a hospital, finding out what the problems are, and then thinking about all the mechanical solutions you've already seen that work, and then tying the two things together.
It's a great answer. Yeah. I know for myself, I like attending generalist conferences and just poking in to see what are the current innovations in different fields and then taking them ideas away. Yeah.
Absolutely. Yeah, that's a great way to do it.
Yeah. Another one, you're talking about sensors to adapt the heart rate. And I was curious, is there anything happening like at the moment? For instance, can patients or clinicians manually adjust the heart rate, for instance, through settings on a phone or something? Or is there, instead of internal sensors, a way of using external sensors as a temporary sort of thing?
Yeah, so there's not really a way to adjust it sort of on a regular basis. At the moment, the way it's adjusted is the patients come in for their inpatient visit, every few months, for instance, and then they might get their speeds adjusted depending on what they need, or if they're having any complications, and they can come in and get it adjusted. As far as developing other sensors, there is an implantable pressure sensor called the CardioMEMS device, but it's not a continuous pressure sensor. It relies on a monitor being placed outside to actually power it up to read what the pressure is. But the company that has that, Abbott, are working on making that a continuous pressure sensor for input into the devices. The option of using external sensors or estimators is also an option. We've developed estimators based on things such as the current that the pump draws, the power, the waveforms that we see in the pumps, things like that, that give us an estimation of what those pressures might be. But those estimations are not perfect. And if you think about it, like if the estimation gets it wrong and the device does something that it really shouldn't and it kills the patient, then it's kind of the fault of the manufacturer. And in that case, the litigation then, or the lawsuit potentially goes against the manufacturer, which is obviously a really big risk for the manufacturer to adopt that. Other external sensors such as accelerometers are also things that people are considering employing, but just there's not been enough work done on that yet.
Yeah. I'm trying to think. We might have had a talk. There is, I know we talked about software, which is, there is actually a lot of work happening in regulations for software and making it more like they are a clinician in itself. So there isn't major lawsuits. Less familiar with the manufacturer side. Another question was, could you shine some light on the projects that you've done during your journey?
Yeah, sure. So many. Lots and lots of technical projects. I'm kind of one of the people that's like a kid in a candy store, and I just run around and get so excited by everything in this field. So I've been involved in quite a lot of projects, but particularly major projects include, I have written the biggest book in the world in this field. It's called Mechanical Circulatory and Respiratory Support. And I'm the lead editor on that. So that was something that used about 1.5 years of my life. I've been involved in the development of artificial hearts. I've been involved in ventilator splitting during COVID times, and that was implemented clinically, and even in the assisting development of low-cost ventilators during COVID as well. So I've adapted my cardiovascular engineering into substantially different applications as well. I've developed surgical techniques, I've developed clinical training devices, and I've translated a lot of these into practice, into changing the way that we treat patients, changing the way that clinicians do things, which is always some of my favorite things. But honestly, probably my biggest success in my entire career is the people that I've mentored throughout their journey. I've been very lucky to have many brilliant people in my group, some students that are just mind-blowingly good. My motto is always to employ people that are smarter than me and then give them the opportunity to shine and support them in doing that. And by far, definitely the biggest, most rewarding projects are definitely the people that I've helped.
I think this will be a final question, which was on, can someone who is a beginner in biomedical engineering join the Heart Hackathon?
Yeah, absolutely. We encourage it. So we have, a lot of our student teams are very young biomedical engineering students. I don't think we have any age limits at all on it. Undergraduates are really strongly encouraged to get involved and even, get involved in Heart Hackathon and get involved in cardiovascular research as well. No matter where you're from, if you're from Australia or overseas, you're welcome to even get in contact with me and come and do an internship in my lab. Or in a laboratory near you. So definitely reach out, look for all of those sorts of opportunities and grab them with both hands, because it can really define your whole career getting involved in stuff like this.
Definitely. Yeah, so for the Heart Hackathon itself, one is finding an advisor that can support you through the Heart Hackathon competition. And if it is potentially not possible that you can't form a team or you don't feel ready, you are still able to attend the webinars and all that, and then potentially create a team when you're more senior as well. As there is no more questions, thank you very much for sparing your time, sharing your insights in your journey, the various developments in total artificial hearts, and the Heart Hackathon competition.
Wonderful. Thanks so much, Ethan, and thanks everyone for joining. Cheers.